Hello, you're welcome to this tutorial. In this video, you're going to learn how to solve system of linear equations using Gauss-Seidel Iterative procedure. So the question says that we should solve the following system of linear equations correct up to 3 decimal places using the Gauss-Seidel Iterative procedure. So it says that we should take the zero vector as the initial solution vector, and then we should show that at the fifth iteration, the solution is correct to 3 decimal places. The exact solution is the exact solution for the system is x1 equals 1, x2 equals 1, and then x3 equals what 1. Okay, so we've been told that the exact solution for this system is x1 equals x2 equals x3, and then they are equal to what 1. So we're going to use Gauss-Seidel iterative procedure to prove this. So what we do is that for the first equation, you will make x1 the subject, and then for the second equation, you will make x2 the subject, and then for the third equation, you will make x3 the subject. So we've been given the initial approximations as a zero vector, which is this value that we have here. Okay, so we start with the first variable x1. So we're going to substitute the initial approximation for x2, which is 0 here. So we're going to put 0 here, and then we put 0 here also. So when you do this, we're going to get x1 to be 1. Okay, so now we compute uh, the first iteration value for x2. Okay, so that one we're going to have 1 over 4 multiplying 7 minus 2x. Okay, and then you see that here we are using the first iteration value. Okay, we are using the first approximation value for x1, which is what 1, and not the 0. Okay, if it was Gauss-Jacobi, we are going to use 0 here. Okay, because the initial approximation given what was 0, but for Gauss-Seidel, okay, we are not going to use the 0. Okay, we will use the new value for x1 that we found, which is what 1. Okay, so we are going to put 1 rather here. So in that case, you're going to have x2 to be equal to, okay, x2 to be equal to 1 over 4, okay, multiplying 7 minus 2x1. Okay, so you're going to use the first approximation for x1, right? Not the initial approximation, which is what 0. So in using the first approximation, that would be what 1, because you got 1, which is this one here, right? Minus x3. x3 is still 0. Okay, x3 will still be what 0. So just put our 0 here. So at the end, you're going to have 1 over 4 multiplying 5, right? So at the end, you're going to have 5 over 4. So you're going to have 5 over 4, okay, which will give us the in the first approximation for x2 to be 1.25. So now that means that the next variable that we are going to solve for, we are going to consider x2 to be what 1.25, and then x1 to be what 1. We are not going to consider x1 to be 0, and then x2 also to be what 0. This is Gauss-Seidel, so that's how it is done. If it was Gauss-Jacobi, we're still going to use the zeros until we get completely new values for all the variables. Then we use it for the next approximation. Okay, so now if you want to find x3, okay, we are going to have the first approximation for x3 to be equal to 1 over 4, okay, multiplying 4 minus x1. Okay, so we know that we're not going to use x1, which is what 0. We're going to use the new value, which is what 1, right? So we're going to have 4 minus 1, and then plus x2, which is now at 1.25. We're not going to use 0. We're going to use 1.25. Okay, so let's find the value. So I'm going to get 1 over, I'm going to get 1, let me set this again. I'm going to get 1 over 4, okay, multiplying 4 minus 1 plus 1.25. Okay, so this will give us a value of 1.0625 for the first approximation of what variable x3. Okay, so I'm going to use these approximations to get the next approximations. Okay, so for the next approximations, we have x1, which is the second approximation for x1. You're going to have 1 over 3, okay, multiplying 3 minus the first approximation for what x2, right, which is what 1.25. So I'm going to have 1.25 plus the first approximation for what x3, which is what 1.0625. 0.625, right? This is what you're going to have. So let's see what you're going to get. So you have 1 over 3, okay, multiplying 3 minus 1.25 plus 1.0625. This will give us a value of 0.9375. So 0.9375. Okay, so for this one, for accuracy, I would advise that if you can write all the values you get, just write it. Okay, don't run anything. Okay, I tried running it my previous video on the Gauss-Jacobi method, and then it actually changed the values a little bit. So I would advise that if you can write all the values, then just write it down. Okay, so now this becomes the second approximation for x1. Okay, so that means that wherever you are going to see x1, you are now going to use this value 0.9375. You are not going to use this x1, which was 1 again. You're not going to use that 1 again. Okay, so let's look at x2. So the second approximation for x2 will be 1 over 4. Okay, multiplying bracket open 7 minus 2, multiplying the second approximation, okay, for x1. You're not going to use the first approximation, which was 1. You're not going to use the second approximation, which is what, 0.9375. Okay, so you see how it's done. So you're going to have minus what, x3. You've not gotten a new value for x3 yet, so you can still use the old one. So that was minus 1.0625. Okay, so let's see what you're going to get for the second approximation of what, x2. So you're going to have uh, 1 over 4 multiplying 7 minus 2 multiplying 0.9375, okay, minus 1.0625. So this also gave me a value of 1.015625. So let me end it here. Okay, 1.0156. Okay, this is a little long, so I just try to shorten it here. Okay, so this will be the second approximation for x2. Okay, so let's take notes of this. So anywhere we see x2 now, that's the variable, that's the value you are going to use. So I'm going to have the x3, okay, to be equal to 1 over 4 multiplying 4, okay, minus the second approximation of what, x1, which we have to be 0.9375. So 0.9375, okay, plus the second approximation of what, x2, which is what, 1.0156. Okay, so now let's see. So we're going to have 1 over 4, okay, multiplying 4 minus 0.9375 plus 1.0156. So this will also give us a value of 1.0195. Okay, so this is what you are going to get. So you continue. Okay, the question says that we should show that at the fifth iteration the solution is correct to what, 3 decimal places. What this means is that if we iterate up to the fifth iteration and then we run the values to 3 decimal places, that should give us the actual solution. Okay, so you continue this to the fifth iteration. So they did that here. Okay, they did that here, and then this was the fifth iteration. Okay, so what we will have to do is that when we get to the fifth iteration, we will try and round the values there to 3 decimal places. Okay, and then what the question says is that the answers you will get should satisfy the equation. So when I run 0.9999 to 3 decimal places, you are going to get 1. So that means our x1 will be equal to 1, and then our x2, okay, this one also will be equal to 1 after running it to 3 decimal places, and then you're going to get x3 also to be equal to what, 1. So at the end, this will be the solution. Okay, this will be the solution. So even if you continue to iterate, you see that you continue to get 1 throughout, 1 throughout. So for the sixth iteration, you got 1 throughout, and then the seventh also you got 1 throughout. So that tells us that x1 is equal to 1, x2 is also equal to 1, and x3 is also equal to what, 1. So comparing this method to the Gauss-Jacobi method. Okay, you will see that this method is a little shorter than the Jacobi method, because from the previous example that we solved, okay, we use the same equations, okay, but for the Gauss-Jacobi, we iterated for about 10 times before we started getting the actual values that we wanted, okay. But you see that for the Gauss-Seidel, as soon as we got to the fifth iteration, we were getting the answers that we want. Thank you very much for watching this video.